Okay, good afternoon, students. Welcome to the real analysis lectures. So, in a previous session, we have defined what is closed set and some of the examples and some theorems like arbitrary intersection of closed sets is closed, but arbitrary union of closed sets need not be closed. Okay. Now, next theorem we will define. I will state next theorem. In a discrete metric space, every subset is closed. Every subset is closed. We already proved if MD be a discrete metric space, every subset is open. Okay. Similarly, we can prove every subset of a discrete metric space is closed. I will write this as every subset of a discrete metric space is closed. And already we have proved every subset of a discrete metric space is open. So we can say every subset of a discrete metric space is clopen. Clopen means it is open as well as closed. Okay. So for how we will prove this? Let A is any arbitrary subset of M, where M is a I will say MD, where MD is a discrete metric space. Discrete metric space. So, since every subset of discrete metric space is open, A complement also must be open. A complement, which is a subset of again metric space MD, is also open. So this implies A must be closed. A is closed set. Okay. So now next theorem. I will state in a metric space, every finite set is closed. Okay, whatever may be the metric space, every finite set is closed. So again we will prove this. So let MD be a metric space and say finite set means we will denote let and say x1, x2, xn be any subset of MD, this metric space. And what is my claim? This x1, x2, xn is closed. I want to prove this finite set is closed. We know that this if it is a finite set, it can be written as union of singleton sets, right? Which is nothing but I will write this as, here only we can write, which is nothing but or instead of this I will write x1 this can be written as union I is equal to 1 to n xi I is equal to 1 to n xi. So it is In yesterday's lecture, we have already proved that finite union of closed sets is closed. So if we prove every singleton set is closed and this is nothing but finite union, so I can say that this finite set is also closed. Okay, so since finite union of closed sets is closed, it is enough to prove that every singleton set is closed. So my claim is every singleton set is closed. So let X be singleton set. So let X be any subset of any singleton subset of M. And what is my claim now? I want to prove M minus singleton X is, or claim this singleton X is closed. That is, I want to prove M minus singleton X is open. Okay, so how we prove usually open set? So let start with arbitrary point y belongs to M minus singleton X. Now since X is not in M and y belongs to M minus X, what is the distance between X, Y? This implies y must not be equal to X. So what is distance between X, Y? This implies distance between X, Y must be strictly greater than 0. So let epsilon is equal to this distance of X, Y. Then X does not belongs to B epsilon of Y, as epsilon is nothing but distance of X, Y, and which cannot be less than epsilon. Therefore, B epsilon of Y is contained in M minus singleton X. So Y belongs to B epsilon of Y, which is contained in M minus X. Therefore, this M minus singleton X is an open set. That is, this implies singleton X is closed. So this proves the theorem. Okay. Okay. Now next we prove a theorem. Next theorem. Given a set F in metric space MD, the following statements are equivalent. The following statements are equivalent. What are that statements? First, F is closed. Second, if B epsilon of X intersection F is not empty for every epsilon greater than 0, then X must belongs to F. And third, if a sequence xn in F converges to X in M, then also X must belongs to F. Okay, so we want to prove these three statements are equivalent to each other. Means 1 implies 2, 2 implies 3, and 3 implies 1. Equivalent means 1 implies 2, 2 implies 3, 3 implies 1. So cycle will be complete. That is equivalent. That is, we can write here, or we want to prove 1 implies 2, 2 implies 3, and 3 implies 4, like that. Its cycle should be complete. Okay, so one by one we will prove. Suppose f is closed. So we prove 1 implies 2. Okay, so suppose f is closed. F is closed subset of metric space MD. And what we want to prove? If B epsilon of X intersection F is non-empty for every epsilon greater than 0, then we want to prove X belongs to F. Okay, so and also assume B epsilon of X intersection F is not empty for every epsilon greater than 0. So I want to prove now X belongs to F, but so on the contrary, assume what is my claim here? X belongs to F. So on the contrary, assume X does not belongs to F. If X does not belongs to F means what? It belongs to F complement. This implies X belongs to F complement, and F is closed, so F complement is open. So, and since F complement is open, what will happen? There exists epsilon greater than 0 such that B epsilon of X is totally containing F complement, right? So this implies B epsilon of X intersection F must be empty, and which is contradiction. Is that right? Therefore our assumption is wrong, and X must belongs to F. Therefore X must belongs to F. Now we want to prove 2 implies 3. Now we prove 2 implies 3. What is statement 2? If B epsilon of X intersection F is non-empty for every epsilon greater than 0, then X belongs to F. And what we want to prove? If a sequence Xn in F converges to X in M, then also X belongs to F, we want to prove. Okay, so we will start. Let Xn be a sequence. Xn be a sequence in F. Let Xn be a sequence in F such that Xn converges to X for some X in M, and let epsilon greater than, I want to show now X belongs to F. So let epsilon greater than 0. Since Xn converges to X, what will happen? For this epsilon greater than 0, there exists natural number n belongs to natural number n such that distance between Xn and X is less than epsilon for all n greater than equal to this n. So what this implies? Xn belongs to which ball? B epsilon of x for all n greater than equal to n, right? So, but where is this xn's? Where are these xn's? Xn's are in F. So what can I say? Xn belongs to xn belongs to B epsilon of x intersection F for all n greater than equal to n. So what this implies? B epsilon of x intersection F is non-empty. Intersection F is non-empty for every epsilon greater than 0, right? So what this from 2, x must belongs to F using 2, okay? Now I want to prove this 3 implies 1. Third statement implies 1. Statement implies 1. Means assume third statement is true and prove that first is what? F is closed. So we want to show to prove F is closed. So in order to prove we will prove F complement is open. Okay. So how again we will show it is open? On the contrary, assume F complement is not open. On the contrary, assume F complement is not open. Okay. If M complement is not open, then there exists X belongs to F complement such that B epsilon of X does not contain in F complement for every epsilon greater than 0. So in particular, for epsilon is equal to 1 by n, also there exists some xn belongs to this ball of radius 1 by n, but xn does not belongs to F complement, right? So this implies xn belongs to b1 by n of x and xn belongs to F. Xn does not belongs to F complement, means xn must belongs to F, right? So this implies xn converges to x and xn belongs to F. So from third, x must be in F, but which is contradiction because where we started, there exists x belongs to F complement we have started, which is contradiction to right here, okay, which is contradiction to x belongs to F complement. Therefore our assumption is wrong. Therefore F complement is open. Therefore F complement must be open, that is F must be closed. F must be closed. Is that okay? So this theorem is also very important because many times we will use this equivalent statements. Once again we will recall these statements. F is closed. This implies if B epsilon of x intersection F is empty, is not empty for every epsilon greater than 0, then we can say x must be in F. And if there is a sequence xn in F converges to x in M, then also x is in F. Okay, these three statements are equivalent to each other, and this completes our closed set. Now we will define next point as interior point. Interior point. Okay. Interior point. What is mean by an interior point? Interior point, let A first we let A be a subset of M. Then a point, we will define this. Then a point x belongs to A is called interior point. Interior point of A if there exists epsilon greater than 0 such that B epsilon of x is contained in A. And the set of all interior points, the set of interior points of A is denoted by A interior or interior of A. Okay, this A interior, this is the notation interior of A. In fact, interior of A is nothing but x belongs to A such that B epsilon of x is contained in A for some epsilon greater than 0. Set of all x in A such that B epsilon of x is contained in A for some epsilon greater than 0, means x is an interior point. Okay. Note that interior of A is the largest open set. Okay, by definition only we can see it is the open set, but it is the largest open set contained in A. Note that remark we can have. Interior of A is the largest open set contained in A. That is, we can write it, that is interior of A can be written as union of U is open and what is such that U is contained in A. Union of open balls is open set. Okay, so it is the largest open set contained in A. So we will see some examples. First, let A is equal to close interval 0, 1. Find interior of A, or show that interior of A, then A interior is nothing but open 0, 1. We want to prove that it is open interval 0, 1. So how we will show, means we want to prove every point of open interval 0, 1 is an interior point of A. So you can easily prove this. Let x belongs to open interval 0, 1. We will show that, then we show that, or our claim, then claim x is an interior point of A. Interior point of A. Why X will be an interior point of A? How we can say by definition? If we can have some open ball which is totally contained in A, for which X is the center, then we can say it is an interior point. So can you give me an open ball of some radius? Since 0, 1 is an open set and X belongs to 0, 1, there exists epsilon greater than 0 so that B epsilon of X is contained in 0, 1, right? B epsilon of X is contained in 0, 1, but what is B epsilon of X? X minus epsilon, X plus epsilon, right, which is contained in 0, 1 and which is contained in closed interval 0, 1. So that is, or I can write therefore X belongs to B epsilon of X which is contained in A. Therefore A is nothing but my 0, 1. Therefore X is an interior point of close interval 0, 1. What about 0 and 1 points? As now X is equal to 0 and X is equal to 1 are not interior points. Why they are not interior points? Because you cannot find a ball which is totally contained as for any epsilon greater than 0 minus epsilon epsilon this ball, and what is the ball around 1? 1 minus epsilon and 1 plus epsilon which does not contain in closed interval 0, 1. Therefore which is nothing but my A. Which is nothing but my A. Therefore interior of A must be only open interval. Therefore interior of A is nothing but open interval 0, 1. Okay. In general, what is interior of closed interval AB? Closed interval AB is nothing but open interval AB. Is that right? In similar lines we can prove that okay, so X is equal to 0 and X is equal to 1 are not interior points because we cannot have a open ball which does not contain in closed interval 0, 1. Therefore interior of A is open 0, 1. Similarly we can prove that interior of closed interval of AB is nothing but open interval AB. Okay. Now next thing, we can have as a remark, if A is contained in M which is open, then what is interior of A? Must be A, right? Because A is the largest open set contained in A. Therefore interior of A must be equal to A. Other example, next example, if A is equal to 1 by n such that n is greater than equal to 1, then what is interior? Interior of A is equal to empty set. Why? If A is equal to this set 1 by n greater than equal to 1, then we want to prove interior of A is empty set, means there is no interior point. Because for any x belongs to A, there does not exist epsilon greater than 0 such that x minus epsilon means x minus epsilon and b epsilon of x, that is nothing but x minus epsilon x plus epsilon, which is totally containing A, as this x minus epsilon x plus epsilon contains some irrationals also, right? Contains irrationals, whereas A does not. Therefore, interior of A must be empty set. We know that every open interval, whatever may be small, it contains rationals as well as irrationals. Okay, we already proved it. Okay, set of rationals and set of irrationals, they are dense sets. Okay, now next example, you can write this as first, second. These are very important. Similar lines. What should be interior of n? Interior of set of natural numbers as well as interior of z, which is nothing but interior of q, which is nothing but interior of r minus q. These are nothing but empty set. Means there is no interior point for set of natural numbers as well as set of integers as well as set of rational numbers as well as set of irrational numbers. There is no interior point. Why? Again the same thing, because for any epsilon greater than 0, b epsilon of x does not contain in that set. Okay, because whatever may be the small interval, it will contain, if it is set of natural numbers, it will contain rationals, we can say. Set of integers also we can say set of rationals. If it is set of rational numbers, we can say it contains irrational numbers. Okay, so it must be, we can write, otherwise we can write over here let A is equal to n or z, same proof. Okay, or q, then for any x in A and for any epsilon greater than 0, b epsilon of x, what is that? X minus epsilon x plus epsilon does not contain in A, because it contains irrationals. Contains irrationals, whereas A does not. Whereas A does not. Okay. Therefore, x is not an interior point. Therefore, x is A has no interior point. What about for q complement? Q complement means r minus q. If A is equal to r minus q, what can I say? Then for any x in A and epsilon greater than 0, x minus epsilon, x plus epsilon contains rational numbers, okay, contains rational numbers, whereas A does not. Therefore, interior of A must be empty set. Okay. Okay. So now next we define. We already define interior point and examples. Now we define closure of a set. Next one we will define as closure of a set. Closure of a set. Let A is a subset of M. Then closure of A is the smallest set. Is the smallest set let me erase this. Let A is a subset of M, then closure of A is the smallest closed set. Okay, not only the set, smallest closed set containing A. Containing A. It is denoted by A closure or closure of A, CL of A, or this notation A closure. Is that okay? What is interior of a set? It is the largest open set contained in A. Okay. Here we can write what is the relation between A interior and A closure. A interior is the largest open set contained in A, and sorry. What is the relation? A closure is smallest closed set containing A. A interior is the largest open set contained in A. So A closure is bigger. Okay. This is the largest open set. This is the smallest closed set containing A. This is the largest open set contained in A. See, there is difference between contained and containing. Contained in A, and this is smallest closed set containing A. Containing A. Okay. Okay. Clearly, we can write here also. We can write A closure, or that is A closure can be written as, it is the smallest closed set. So intersection F is closed. And how is this F? F A is contained in F. Okay. Smallest closed set containing A. Now next definition. clearly we can say this. Clearly A interior is contained in A and containing A closure. Okay, is contained in A closure. Now next definition we will write limit point. What is a limit point? Let A is a subset of M, then any point x in M is said to be a limit point x belongs to M is said to be a limit point of A if every neighborhood of X contains a point of A other than X, contains a point of A other than X, that is B epsilon of X, this is neighborhood of X, and does not other than X means we will remove that X from here. So contains a point of A means intersection of A is non-empty for every epsilon greater than 0, because every neighborhood we are saying. Okay, so that is B epsilon of X minus this singleton X, intersection A is non-empty for every epsilon greater than 0, then this X is called as limit point of A. Okay, again we can have a remark. The set together with all limit points, the set A together with all limit points of A is the closure of A, is the closure of A. That is, A closure is nothing but A union all limit points of A. Limit points of A. Okay. A closure is nothing but A union whatever limit points of A. So, for example, let A is equal to open 0, close 1. So 0 is the limit point of A here. Therefore, what is A closure? Then A closure is nothing but close 0, open 1. Since 0 is the limit point of A. Okay. Second, A is equal to open interval 0, 1. Then what is A closure? Now 0 and 1 both are limit points. So close interval 0, 1. Since 0 and 1 are limit points of A. And third, take A is equal to 1 by n such that n greater than equal to 1. Then what is limit point of this? Limit is 0. So A closure is nothing but A union singleton 0, as 0 is the limit point of A. Is that okay? Now, after this definition and examples, we see some theorems. Theorem: X belongs to A closure. In any metric space, X belongs to A closure if and only if B epsilon of X intersection A is non-empty for every epsilon greater than 0. How will prove this? Suppose X belongs to A closure. Suppose it is if and only if statement, X belongs to A closure. And on the contrary, assume, by contradiction we will prove, on the contrary, assume there exists epsilon greater than 0 such that B epsilon of X intersection A is empty. Okay. So what this implies? A is contained in which set? B epsilon of X and its complement it will be contained. And how is B epsilon of X complement which is closed? Since B epsilon of X, because B epsilon of X is open, so its complement must be closed. Since B epsilon of X and its complement is closed, and A closure is the smallest closed set containing A. What can I say? Containing A. What can I say about A closure and B epsilon of X complement? A closure is contained in B epsilon of X and its complement, right? Because it is the smallest closed set. Now, what this implies? Since X belongs to A closure, since X belongs to A closure, this implies X belongs to B epsilon of X and its complement also, right? So what this implies? X does not belongs to B epsilon of X, which is contradiction. Which is contradiction. Therefore, our assumption is wrong, and hence B epsilon of A, for every epsilon greater than 0, B epsilon of X intersection A must be non-empty. Okay. Therefore, B epsilon of X intersection A must be non-empty for every epsilon greater than 0. Now, conversely, assume that assume this is non-empty. B epsilon of X intersection A is non-empty for every epsilon greater than 0, and what we want to show? X belongs to A closure. Now, suppose B epsilon of X intersection A is non-empty for every epsilon greater than 0. So this implies B epsilon of X intersection A closure is also non-empty, because A closure is bigger than A, right? You can write here, since A is contained in A closure. So what this, we all, since A closure is closed set, A closure is closed, we already proved that three equivalent statements, from that we can say that X must belongs to A closure, right? X belongs to A closure. From the theorem we have already proved. Okay. This only we want to prove. So next corollary we can have one corollary. Corollary: X belongs to A closure if and only if there is a sequence xn contained in A such that xn converges to X. So if we take X point in A closure, then there must exist a sequence in A which converges to that X that we want to show. And conversely, okay, so proof: let X belongs to A closure. So if X belongs to A closure, B epsilon of X intersection A is non-empty for every epsilon greater than 0 by above theorem. Right? So in particular, for epsilon is equal to 1 by n, there exists xn belongs to B epsilon of X, right? Intersection A. So what this implies? Epsilon is equal to 1 by n. Okay. There exists xn belongs to B epsilon of X intersection A. So this implies xn belongs to B epsilon of X and xn belongs to A also. So xn, what is distance between xn and X, which is less than epsilon? Epsilon is nothing but my 1 by n. Right here 1 by n. It's less than 1 by n and xn belongs to A. So what this gives me? This implies xn converges to X. So there exists a sequence of elements in A. Therefore, there exists a sequence xn in A so that xn converges to X. Okay. Conversely, assume there exists a sequence xn in A so that xn converges to X. And what I want to prove? X belongs to A closure. So let xn be a sequence in A such that xn converges to X. And I want to prove X belongs to A closure. So given epsilon greater than 0, what will happen? By convergence, there exists natural number n belongs to n such that what? Such that distance between xn and X is less than epsilon for all n greater than equal to this n. So what this implies? Xn belongs to B epsilon of X for all n greater than equal to n. But where is this xn? Xn belongs to B epsilon of X intersection A for all n greater than equal to n. So this implies xn belongs to B epsilon of X intersection A for all n belongs to n, means this is non-empty, right? So this implies B epsilon of X intersection A is non-empty, not empty for every epsilon greater than 0, right? So what this implies? This implies X must belongs to A closure. Okay, again by theorem. Okay, so this completes our close set, interior point, and closure of a set, limit point as well as closure of a set. Thank you.